Hi everyone. Today I'll be talking about self-stabilizing leader election. My name is Ho-Lin, and this is joint work with my student Hsueh-Ping. We are from National Taiwan University. Our talk will be focusing on a distributed computation model called population protocols. Population protocols is basically describes a large set of identical and anonymous agents, and these agents can only perform pairwise interactions. There are many different application fields which the population protocols can apply. For example, previously I've been working on computation using molecules. When we have a large number of molecules in a solution, if we treat each molecule as an agent and the type of the molecule as its internal state, then molecular reactions can be perfectly described by population protocols. And so if we want to talk about the computational power of chemical reaction systems, we can talk about the computational power of population protocols. Population protocols can also be used to describe the interaction between a flux of animals, interaction between a large number of robots, or the interaction between a large number of small sensors. So now, let me give a slightly more detailed description on population protocols. In a population protocol, we have a large number of agents, and each of them has a finite internal state. Each two agents react with each other and change states according to a predefined transition function. Usually we assume that we can program this transition function arbitrarily. Okay, and after that, we have another two agents react with each other and change states. And this process will go on forever. Usually we assume that the sequence of reactions is actually chosen uniformly at random or satisfies some kind of global fairness. And our construction works for both cases. Now, in this talk, we'll be focusing on a special task called leader election. In the leader election, given the initial state, we want the system to eventually reach a safe configuration with only one agent in the leader states. So we are going to define some of the states being leader states, some other states being non-leader states. So eventually, the system is going to reach a safe configuration with only one leader. And we would like to keep this unique leader forever, meaning that this particular agents will now, from now on, this particular agents will stay in the leader state forever, while all the other agents will stay in the non-leader states. For most previous works on leader election, we assume that all agents start with the same initial states. And there are many previous works on this. In particular, a protocol published in Stock 2020 this year has already achieved optimal time and optimal state space at the same time. In this talk, we are looking at a different variation called self-stabilizing leader election. In a self-stabilizing leader election, we allow these agents to start with arbitrary states. It can start with no leader, it can start with multiple leaders, but eventually we still want them to reach a safe configuration with a unique leader and then keep this unique leader forever. However, it is previously known that self-stabilizing leader election is not possible without extra information if we allow every two agents to talk to each other. So instead of looking at the general case where every two agents can talk to each other, we are looking at a particular case where there is an underlying communication graph, such that every agent is a node, and every node, can only talk to its neighbors. Okay, they are still anonymous, and the agents still have no knowledge about this communication graph. But whenever we pick two agents to interact, they must be neighbors of each other. Previously, self-stabilizing linear election has been studied on rings, directed rings, where agents form a fixed ring structure. In 2008, when the idea of self-stabilizing is first studied on propagation protocols, there's a protocol, there's a SSLE protocol proposed on all rings of odd sizes. So it's a single protocol working for all different ring sizes as long as the sizes are an odd number. Last year, we have extended the result into an SSLE protocol which works on rings of arbitrary sizes. So it's the same protocol which works on arbitrary ring sizes. And both protocol uses a constant number of states. In this work, we are going to extend the previous constructions on rings into self-stabilizing linear election protocols on arbitrary k-regular graphs. Okay, it's a different protocol for every k, but the same protocol will work for every k-regular graph. We have a single protocol that works for every regular graph of degree k, regardless of the size of the graph. So today I'm going to describe two different protocols which are able to do this. The first one is a virtual ring protocol, which is much simple and more intuitive, but requires a large number of states. The state requirements is omega of k to the k. The second is a much more complicated spanning tree protocol, which we are able to reduce the number of states to order of k to the 12th. So notice that this number of states only depends on the degree of the nodes, and it works for graphs of arbitrary sizes. Okay, so first, let me describe the virtual ring protocol. In the virtual ring protocol, we are given a k-regular graph, and as a first step, we are going to double the number of edges. Okay, and then we are going to divide each node into k virtual nodes arbitrarily, with every virtual node having exactly two edges connecting to the external, connecting to its neighbors. Okay, notice that this division is only virtual. So basically you can imagine that there's an agent, a single agent, whose internal state can be divided into 12 different fields, and each field corresponds to the internal state of one virtual node, of one virtual agent. Okay, so this particular node, this particular single node still knows the state of all of the k different virtual nodes. So if we do this for an arbitrary k-regular graph, we are going to have a much larger graph, a graph of k which is k times larger, but every node has degree 2. Eventually, this just breaks the whole graph into a collection of different virtual rings. Okay, notice that these virtual rings are still connected together. All virtual nodes of the same color actually correspond to the same agent. So there's a single blue agent which knows the exact state for all the blue virtual nodes. There's a red agent which knows all the states for all the red nodes, and so on. Okay, but since we have decomposed the whole structure into a collection of rings, now we can use the self-stabilizing linear election protocol on rings to elect a leader on each of the rings. Okay, and after a leader has been elected, the leader can send out tokens, and tokens will circulate around the grid. So if we have two tokens, they actually meet each other, meaning that two tokens going to they actually happen to travel to two virtual nodes of the same color, then a particular node will immediately see that there are two different tokens circulating in the system, meaning that there are at least two virtual rings. In this case, this node will now reset the whole system by sending out a reset signal. Okay, so now after a reset signal has been sent, after a node has received a reset signal, it resets all the settings for the virtual node. It tries to connect the virtual nodes in a different way, and the system basically restarts. Essentially, we can see that the only way that this system can stabilize without resetting is that there's only one virtual ring, one leader, and one token. Okay. Of course, if initially the system tries to stabilize into one virtual ring, in the process of the leader election, there could still be multiple leaders, multiple tokens in the beginning, causing the system to reset. But eventually, after many resets, possibly, the system this is the only stable state. Okay, so whenever the system stabilizes, we can guarantee that there's only one virtual ring, one leader. Okay, and the actual node which corresponds to this leader virtual node is the leader of the whole system. And this completes the first protocol, the virtual ring protocol. As you can see, in this virtual ring protocol, each node must remember the actual internal states for k different virtual nodes. And each of these virtual nodes may have up to k states. So the actual state requirement for each node in this virtual ring protocol is very high. It can be up to omega of k to the k. So in the second protocol, we are making a different proposal which can reduce the number of states down to order of k to the 12th. And we call this a spanning tree protocol because in general, instead of trying to form virtual rings, now we are trying to form spanning trees for the original input word. So now in the spanning tree protocol, we no longer have nodes dividing the virtual nodes. So now each node only picks one neighboring node as its parent, arbitrarily. So it could also pick itself as the agent, which means it is the root. Okay, so ideally we would like to make one single spanning tree, and the root of the tree is the leader. Of course, when every node picks the parent arbitrarily, many bad things can happen. For example, we can have zero leader at all. In this case, there must be a cycle somewhere. Or we can have multiple leaders, which means there are multiple trees with multiple roots. In the first case, we deal with cycles by using the self-stabilizing leader election on rings, because by applying this particular protocol, we can guarantee that every cycle will eventually be broken. Eventually, whenever we have a cycle, eventually there will be one node being elected as the leader, and the leader will now have a pointer pointing to itself instead of one of its neighbors. Okay, so in the final final configuration which stabilizes, there will never be cycles. We are guaranteed to have a structure of trees or forests. Now, in the case of multiple routes, we can do similar things to the previous protocol, which basically will allow each leader to send out tokens that circulate in the tree. Okay, so we have to have special designs for these tokens. These tokens have to now traverse this tree thoroughly. So if we can do that, when we have multiple routes, when they send out tokens, eventually two of the tokens will go to neighboring nodes and they will see each other. And when two tokens see each other, they can reset. Okay, so we reset. We deal with the first problem where there's no leader by self-stabilizing leader action on rings. We deal with the second state, second problem where there are multiple leaders in the system by leaders sending out tokens and reset the system. Okay, so eventually, when the system stabilizes, we can only have one leader, one single spanning tree, and one token. With this idea, we are able to reduce the number of states down to order of k to the 12th. Okay, there are some details that I don't have time to go through, so if you are interested, please refer to our paper. Now, for the self-stabilizing leader election on k-regular graphs, clearly there's still a large room for improvement. For example, first of all, our system, our spanning tree protocol, requires the number of states being order of k to the 12th, which is a large number. On the other hand, the current best known lower bound is k. So, and this is from the result of complete graphs. We know that for complete graphs of size n, each agent must have at least n states in order to do self-stabilizing leader election. Okay, so between k and order of k to the 12th, there's still a big gap there. And we strongly believe that neither of them is the correct bound. So the correct bound should really be somewhere in between, but we don't know where that is. The second question is, what is the convergence time? So as previously mentioned, our self-stabilizing leader election protocol works for both random updates and for arbitrary fair update sequences. Of course, if you only assume fair update sequence, some global fairness conditions, you cannot really have a bound on the time. But even if you assume random updates, our protocol is extremely slow. It will be doubly exponential, at least, maybe worse. Even for a much simpler construction, the ring construction, the convergence time is still very high. It's still a very, very large exponential time. So is it possible to have some self-stabilizing protocol which works for a large class of graphs while being very fast, at least polynomial convergence time? Is something like that possible? This is also a very interesting question to study. Okay, so that's all I'm going to talk about. Thank you for your attention.